things, is it going to be very different? Is it mostly going to be the same? Just one, you know, I could have asked you, he could have given you a bunch of tweets. And here's a huge file of tweets. You know, parse the tweets and just pull up the text, take the text and put it together and do this reword. But I've decided not to ask you to do that in the homework because you know, you've done some text processing already. So you don't necessarily need to. But I'd like you to think about how general is this. Did you really have to change that much, or is it pretty much the same? Gotcha. Okay. Just a minute until it turns 3.
Okay.
The calm before the storm. So let's get started. So welcome back, everyone. So we are so we're starting a new kind of so small section of the class on regression. So this is one of the main techniques in probably like all of day analysis, one of the most useful things you can do. And so we're going to have 3 lectures on it, and this is so this is partially because probably many of you have seen something about regression before. So so how many people have heard of or used like ordinary least squares regression? Oh, okay, good. And so maybe 1 or 2 of you haven't, but that's fine. Kind of like the first half an hour of this lecture, I'm going to review basically everything about basic ordinary least squares regression, and then we're going to say, okay, this is what what you can say about this, but here are the shortcomings, and here are some things that we can so we can do beyond that, right? And so most of the ways this is well, so probably this is one of those kind of this is like one of those very basic techniques that is used widely, and probably the most times it's used is just it's like just the most basic version, but there are some like very cool and very and some very important some very important extensions, and these kind of what's going on with these extensions, which we will dive into in these lectures, I think it's really kind of I think it's really getting at the core of what a lot of the most of like explaining why a lot of the most recent developments in things in things like deep learning are actually working, right? So even though deep learning has a much more complicated model, kind of the basic ideas we'll discuss within regression, I think have a lot to do with explaining why these more complicated models can actually work. So let's start by looking a little bit at just the schedule. So we have the next 3 lectures before break on so just regression. The first one today is going to kind of be an overview of like everything we're going to cover, and then we're going to talk about like extensions like lasso and like matching pursuit, and things that are help you understand what's going on when you actually have a lot of variables and you're not sure what to do with all the variables that you're building your regression out of. And then we'll talk about cross-validation in the third lecture. So hopefully a lot of you have heard of cross-validation. If not, it's kind of an essential, so I covered in case you haven't heard of it, but it's like, it's one of these topics which is just, you know, that is just, you know, that is just so important that it's that's worth covering again. Also I'll probably kind of talk about more than just the basics of like cross-validation and kind of where this fits in to the like whole landscape of if you have some data and you want to make some model on the data or make some decision about a model on the data, like what's the right way of doing this, right? And so there are the ideas of like p-values, which have been in like statistics for like 100 years, and if you use things like p-values correctly, it's, you know, it's so it's fine, but it also has some issues with it, and we'll see that cross-validation it like solves can solve some of these problems, but it does not solve all these problems. And so at the end of the third lecture, we'll have another, if we get through everything I planned, we'll have another discussion on some of these more nuanced points and how this can come up. And there's not necessarily like a right or wrong decision of how to do everything. Okay, and I'll try and say more about the midterm, maybe getting, you know, even more specific what's going to be on that as as we're getting a little bit closer to that. It will cover, it's not going to cover the stuff on regression mostly. Regression, I'll push to covering the stuff on the interim exam as well. And then, just so you're thinking, after break, the intermediate report on the project is going to be due just after break. So you should kind of be starting to do something on that. And I'll say more specifically what I'm expecting after that. After here, in this class after break, we're going to have a peer feedback session in the actual class, and then in this week, all the groups are going to meet with me, and you're going to get some like specific feedback on what to do on the project as well as that. So let's talk about. So there's one point on the homework. First I want to say something about the homework for the frequent items problem. There's a part of this which I think is confusing. I meant to give an example of how to think about this in class, but I just want to start by doing this now. So one of the things you're asked to do is to implement these two algorithms, the Misha-Gries algorithm and the Kalman-Sketch algorithm, and you're supposed to get some sort of estimate for a character, right? And the output of the algorithm is going to be it's going to give you an output like f of b hat, right? So the output of your algorithm is going to estimate the frequency of something like the count of b, and I want you to divide this by n, right? So that if you think of dividing this by n, the total count of the stream, then this is going to give you a percentage between 0 and 1, okay? And you're given this estimate, and then I've asked you these questions about if you put something like so like 20% here, right? Does B then have to be more than 20% of the values, right? So you have to ask a question whether it might be above 20% or if it must be above 20%. And so how we should think about this is I don't know the true value, but I've got an estimate. And so depending on the algorithm, for one algorithm, that means, say if this is 25% is my estimate, then I know the value has to be between 25 and 35%. For the other algorithm, it has to be between 15% and 25%. Okay, so then if I'm saying, might it be above 20%? Well, for one, it might be because for some chance it's less than, some chance it's greater than. The other one, it must be above 25%, right? And so whenever you're asked for these questions of, like an approximation of a certain value, I think it's really helpful to kind of just draw this line out and say, what are the ranges of the value? And then kind of trying to understand that, right? So it's sometimes confusing just to look at it and try and do the algebra, but if you draw this on this line, it's usually easy to figure out what it's asking, and it's hard to make a mistake that way. It's easier to make a mistake if you're just trying to kind of do the algebra in your head. Yeah.
So related to this, you used n instead of n, so like n, which is equal to capital F subscript 1.
Yeah, okay, yeah, so maybe this was m in the assignment.
Right. I'm just wondering when I was looking at it, like, why even have capital F subscript 1 if it's just equal to n? Like, why do you have two variables named like that refer to the same thing?
It's the reason we define this capital F of 1 is because there's been like a lot of work and discussion on the capital F of 2 and the capital F of 0, and kind of it fits in this paradigm. It happens to be exactly equal to the total count of the stream, right? But you can think of it as this overall summary statistic of the distribution. But this one turns out to be obvious, but I could define it for other kind of other values of the subscript, and then those are more meaningful. Yeah.
I just want to check I'm not missing something, but how do you get the range of percentages?
Yeah, so, okay, so there kind of going to be a few things that you do. This value, right, so this value right here is coming out of the algorithm, right? And then there's like, I don't want to give too much information away, but there are two different algorithms. There's the Misch-Agree sketch and there's the count-min sketch. And one of those is always an overestimate, one's always an underestimate. Okay? And the error, I've set up the value that you're doing so that estimate is going to be, the error bounds are going to be off by 10%. Right? So I'm telling you now we're off by 10%, and so that means 25 to 35 or 15 to 25. But substituting in whatever, 25 might be 23.4 or something that you find. Yeah.
I was confused because the one algorithm had, right, for the one algorithm, error is 1 over k, and then the other was 2 over k for the count-min sketch. At least according to the notes. And so
Yeah, but I think you should have set, let me check what I told you to do.
just maybe, yeah.
I think I told you to set it so they're both 10%, but I may have changed it. Oh yeah, yeah, so, right, so, yeah, with the count min sketch, I still said k equals 10, but that k means that the error might be more than 10%. Yeah, good. Good, yeah, so you should factor that in. It might not be 10%, it might be 20%, which I think is the case here. Good. So, okay. So, regression. Good. So in the basic version of regression, so the data is going to be given as x, y, where in the, I'll start with the simple form where x is going to be a vector in R and y is also a vector in R. Okay, and so this will be the explanatory variable, and this will be the dependent variable. And so we'll talk just in a couple of minutes that, you know, you'll often extend, so x is not just one-dimensional, but is multiple dimensional. But what you get is then I can plot x and y here on this axis here, and and so the goal of regression in this case is to fit this data with the line. So I want to fit x, y with a line, and this line, you know, I want to fit it in some way, so somehow the line might go through like this, and this line really is going to be a function from x, so it's going to be a function from x to y, right? So this line is going to give me an estimate of y here. So I'm going to fit this line L. So I'm going to take in a value x. In this case, it'll be some value xi, right? In this case, this is, for instance, this data point here. This is x6, right? So this is yi, xi, right? This line, and it has to be a, you know, the value how you would write a line in this way is a of xi plus b. Okay, and so it's not great here, but this difference here is b, this the value of above 0, and then this slope is a. It's the amount of rise over the run. Okay, so as I increase the x value by 1, in this case maybe I'm also increasing the y value by 1, or something slightly less than 1. In this example, this might be 0.8 xi plus, say, 0.2, right? This b above 0 is 0.2, and it's increasing slightly slower than every increase of x increases the value of y. All right, but I think the most important kind of thing to take away from this picture is that the error is being measured in the difference in the y value. Okay? So basically I'm getting these differences in the y value, and this is my error. This is Ri, right? In the case here, this is R6. And so Ri is going to be, let's say, yi hat minus yi. So what I'm not doing, I'm not measuring the error in this way, right? I could think of measuring the error to be the closest point on the line, okay? I could think of measuring it that way. That's not how I'm measuring the error. I'm only measuring in the direction of the y variable, okay? And this is important because as I put more and more x variables, I have more explanatory variables going on here, then I'm still only measuring in this single direction y. Okay, and so this is going to be of, so a very important observation, and it's going to make kind of a lot of the modeling aspects and the extended versions of these algorithms work easily, actually. So okay, so and so then once I've done this, the goal. So like there are lots of lines I could choose, but the one I want to choose is to so minimize the sum over I of these Ri squared. Okay, so it's going to be minimize these the square of these residuals. Okay, so it's going to be that's why it's called often ordinary least squares, right? So I want to the goal is to find A and B such that the sum over I of the difference from yi minus a xi minus bi, this whole quantity squared. So I want to finding ai so to minimize, over the choice of A and B, this quantity here. Okay, so this is the kind of is the setup of like ordinary least squares regression. Okay, and so it turns out that there's a very simple solution to this problem. So I can write this in a few steps. So the first thing I want to do is to take the average of x. This will be 1 over n if there are n data points. So to take these values, do the same thing with the same thing with the values y, and then I can so describe the covariance of xy as equal to 1 over n times the sum of xi minus minus x bar times yi minus y bar. And so then the optimal solution for A is going to be the covariance of xy divided by the covariance of xx, which is which is just the variance of x, and then B is going to be equal to y bar minus A, once I've solved for this, of x bar. Okay, so I've transformed kind of basically what this is doing is it's forcing, so this is finding the slope, and then so then so there's a simple closed form solution for the optimal values here, right? And so there's you can solve this by just calculating these things, and so this works under this least squares model. So you can also extend this to where if instead your data is often called xy, where now x is going to be in Rn times d, and y is still going to be in Rn. Okay, so it's y is still an n-dimensional vector. Now the data looks like this. So this is x1 up to xn, and I want to, and it's going to have this has d variables. So each xi is now a vector in Rd, and that corresponds with this vector that looks like this. And I'm going to have n of these values. And so I want to find some model now. We'll call this alpha. When I multiply this, this is also part of input, is going to equal to y. And so the size of this y is also n. Okay, so now if I have a variable xi, let's draw this here. So this guy is xi, and he actually looks like xi1, xi2, up to xid. Right? So xi is now xi1, xi2, up to xid. So it's this vector in Rd. So if I go back to this picture, now that I think of this x-axis as actually this d-dimensional space, and I'm predicting this red line is now going to be a red subspace through here, but I'm still measuring the error in this y coordinate. Okay? So I can write the data like this, and an important thing is that there's now this transformation. I'll call this so x tilde, which is going to be, I'm going to kind of extend this. So now this is in R. It's an n-dimensional by d plus times an n-dimensional by a d by a d plus one-dimensional so it's a matrix instead, where now the first coordinate of everything is going to be 1, and then everything before is going to be x1. Then this guy is going to be x2. So now in particular, xi tilde is going to be equal to 1, then xi1, xi2, up to xid. Okay, so I can think of just this guy, I can call this xi0 if I start counting the index from 0. All right, so what this is doing is I'm now created just a one-dimensional thing, and this coordinate actually is going to represent the offset term. Okay, so what's happening is if I look at this model here, this model has d dimensions. Okay, but in this setting I drew up top, I did not have a term for the offset. I did not have a term for this b, which told me where I went off of 0. But I can turn this into a d plus one-dimensional problem, and then this alpha 0 term is basically equal to this b offset term. And I just add some 1s in the front column here, and I'm multiplying the offset always by 1, so I'm just adding it. Just like I'm adding a scalar term to everything in the model. Okay. So now, once I have this, I still want to solve now, his goal is to find this alpha model now in Rd plus 1, which is now going to minimize y hat, or let's say yi, which is still a scalar, minus the dot product of alpha, which is a fixed model, times xi squared. Okay, now alpha is a d plus one-dimensional vector. Each xi tilde is a d plus one-dimensional vector. So this dot product is just kind of multiplying all the coefficients by all the variables. And I look at at the difference from yi, and I square that, and I add those up. I just want to minimize this now. Okay, and so this also has a closed form, a simple closed form solution, and by encoding this 1 in this first column here, it's just a single operation with linear algebra, and I can write this as alpha, the solution is going to be alpha times x tilde transpose, x tilde, the inverse of this, x tilde transpose times y. Okay, this is a closed form solution, the optimal solution for the choice of alpha for this model, which minimizes this sum of squared errors. Okay, before we were doing something like a dot product, which is the covariance here. That's this term, and then we're dividing by the variance or the covariance x to x. And taking an inverse in front is like dividing by this. So it's kind of just an extension of what we did before. Okay, so this is the closed form solution. You could implement yourself if you have linear algebra operations in your programming library, like with MATLAB or if you're using R or with NumPy inside Python. This is very, very simple to do. It's also built in to most things. If you call these squares, it's possibly doing this under the hood if the data size is small. If the data size is large, there might be other stuff that's doing. Or it might still be doing this and it's just taking a long time. So the most expensive part is this inverse operation here. If D is big, then this is inverting a big matrix. That could be an expensive part. Okay, but it has this closed form solution, and it optimally solves this problem, minimizing the sum of the squared residuals for multiple dimensional of these variables. Okay.
Question?
Yeah.
Is it optimized enough to account for outliers in your data?
Yeah, so this is, I haven't talked about outliers yet. I'll plan to talk about outliers in like 10 minutes. Yeah, so this is minimizing sum of squared errors, and if you have one outlier, that's going to cause that the models has to be pulled because I'm just not measuring the difference, but if it's far away, it's that difference squared. And so it really doesn't want these really big outliers in here. So this model is actually kind of susceptible to outliers. And I will give you several ways of dealing with outliers over the second half of this lecture and then the lecture on Wednesday to help you think about that. There's been some recent developments the last 5 years. There are these new kind of techniques that are even better at robustly dealing with outliers. This is the model which is minimizing the variance kind of error in Y, right? So in that sense, this is you can derive this from assuming there's Gaussian noise there, and that's maybe the right thing to do. And some of the other versions don't necessarily optimize that. There are some new kind of models the last 5 years or so that can minimize this after it's filtered out the outliers. And there's kind of some part of this use you identify things far away and throw them away, but there's also some more kind of challenging aspects of there's other ways you can poison the data other than just extreme outliers, but have a bunch of things in slightly the wrong direction. And so they use a lot of tools from this class, but we don't have all of them yet. So maybe I'll talk about this later in the semester. Okay. So this extends naturally to higher dimensions. There's one more extension I want to talk about. So polynomial regression. Okay, and so this is now I want the model m of x, right? So I want my prediction y hat from yi, right, to be instead of a line, I'm going to think of a more complex model. And this is now, we'll just say xi is an r, but you can extend this to multiple variables. But this is now the idea that it's some alpha 0 offset plus alpha 1 xi. So this model is a linear model like we had before, but you can do things like xi squared plus xi cubed, right? And I can keep adding these these polynomial terms, and this gives me a polynomial model. Okay, but I still only have these limited number of these coefficients. As many different powers as I concern, kind of implicitly, this is xi to the power 0, which is always 1. Okay, so as many different powers as I have one coefficient for each of those. You know, if I want to do a different form of regression, I could have done something fun like alpha 4 times sine of xi. I could throw one of these in there as well, if I want to. Okay, but let's kind of just ignore this for now. But the point is, I mean, everything, I can throw in other things like this where I'm learning these coefficients. The insight here is I'm still just trying to learn these coefficients, and the trick is to write this down. So I have this input now, which is just y, or is just this x and this y, where x is in Rd and y is in, or is in R and y is also in R. But I want to map this to an x which is in R, and let's say this is some value p to Rp plus 1. Okay, and so this is going to be a matrix where it's going to have 1 everywhere here in the first column. The next column is x1, x2, up to xn, right? So the height of this still has to be the number of data points I have. Okay, but then this third term is going to be x1 squared, x2 squared, xn squared, up to x1 to the power p, x2 to the power p. Okay, so now this has p plus 1 values here. Okay, and now to solve, the goal is to find some alpha that's in Rp plus 1 that's going to minimize the sum over I of the term yi minus this model, and this model is now j equals 0 up to p of alpha j x I to the power j squared. Okay, so now if I force this as a polynomial model here, well, that corresponds with I've just expanded from a kind of essentially this two variable problem up to a p plus 1 variable problem, and then I can solve it the same way as before. I'll call this x tilde p, and then my solution is just going to be alpha is going to be equal to x tilde p transpose x tilde p inverse x tilde p transpose y. Right? So it's the same optimal solution as before, but now I've handled this polynomial model. Or if I wanted to put sine of xi, well, I could have put a column for that here. So I can fit like any sort of model like this, and this works because I'm only measuring error in this y coordinate, where if I go back to this picture, if instead I wanted some weird polynomial model that went through all these points, if I want some polynomial model that went through these points, well, by kind of extending the x coordinates to higher dimensions, it becomes a linear model in these extra dimensions. Okay, it's the same linear model, and then I can use this multi-dimensional version to solve for it now. okay, so I get this polynomial regression almost for free. I just have to do this expansion. Which might take a little bit of time and space, but it's, you know, for low degree models, it's not so bad. And usually if your data set is really, n is really big, or I mean, if the dimensions are really big, then you probably don't need to do a lot of polynomial expansion, if any. For really high dimensional data sets that start out that way, usually just do a linear model. Only for when you have a really big n but small d, you would do a polynomial expansion. All right. Yeah.
So you're doing that, you have the 1 in the first column.
Yeah.
So when you did that for linear, it was to basically account for,
The offset.
oh.
Because I don't need this to go through the origin, that line to go through the origin, right? If I'm saying, well, I'm doing something like weight versus age, but if when you're born you aren't, if I think your weight is not 0 when you're born, so then, you know, I don't want to start this at 0, right? But there could be other perfectly reasonable things as well, and so it just gives you a richer set of models. If I want to enforce that it goes through the origin, because I want my curve to hit 0 when the x value is 0, well then I just don't solve for this term. And it finds the best model that does not go through the origin. And I can just ignore this column, right? But if I want to allow this offset, then I just add this column. And it automatically folds it into this kind of magical process. Yeah. Okay, good. So this is linear regression, and with the polynomial extension. And in fact, so there's this powerful theorem that's often called the Gauss-Markov theorem that says that that this way of finding this model y, this is this model is optimal in the following 3 conditions are true, right? So if the goal is to the sum of yi minus some model of xi squared. So if my goal is to minimize the sum of the squared errors, okay? So if I assume that the residuals, which are Ri equals yi minus y hat, so if I assume that these are unbiased and so if I assume these are unbiased and they don't have any correlation between them, like if I don't assume that these are unbiased, but I don't know what the bias is, then there's really nothing I can do. If these are correlated in some way, there are kind of some other tricks that will depend on things like dimensional reduction that can try and correct for this under some other more complicated assumptions, but we're not going to discuss these things. So I kind of assume the residuals are unbiased and uncorrelated, right? That means they could be equally above or below 0. And I can look at them individually. The uncorrelated means that they're it's this IID assumption again. And then I want an unbiased so that the solution I want is not going to have any bias in it. Okay. All right. So if these three things hold, I don't want any bias in my solution. I assume the residuals are unbiased and uncorrelated. I can't really do much about that. And the goal is the sum of squared errors, and this is optimal. This is the best thing I can do.
How would you want a biased solution?
Yeah, so, well, that's what we're gonna talk about for a while now. Yeah.
I'm just wondering, when would the residuals be correlated with each other?
You could have, for instance, the larger values of x might have more variance than y. Or you might assume that the data points you have are coming in some sequence. They're not necessarily ordered by the x value, but they're coming in a sequence. And the ones that come later have less error than the ones that came earlier. And so I might, or that it could be the ones that tend to come near each other tend to have similar values, similar error. So that there's some overarching error process that's changing over time but changing slowly. So I could have issues like this, right? So if there is extra knowledge about my data, I may want to factor that in somehow. These assumptions really get into the weeds of the modeling of the problem, and if you really know what they are, then they might not be too hard to factor out. Like I might group a bunch of data points together if I assume that, or use two data points that are too close to each other. Throw away some of my data. There are other kind of lots of different tricks you can try and do to remove this. We're just going to assume that they're uncorrelated, which is almost done everywhere, right? Unless you know something very specific, and then you pre-process your data, hopefully, to avoid this issue. Yes. Okay. So step two, there's not much we can do about. So we're going to usually assume that the residuals are unbiased and are going to be uncorrelated. Okay. Step one is with this sum of the squared errors. And we typically use this there are two reasons that we use this. One, this corresponds with the maximum likelihood estimator for normal noise. If I assume that the actual residuals are built from the model with some normal distribution on the noise about them, which is kind of the most common noise assumption if you're actually building noise or you're trying to observe it, then this is the optimal thing to try and be minimized. This gives you the maximum likelihood. You can define a likelihood using Bayesian techniques, and this one maximizes that likelihood, right? So it comes from there, and there's a good algorithm, namely this guy right here, right? This algorithm is closed form, gives me the optimal solution. So that's why we typically use one. So there are variants. So I'm going to talk about very briefly a couple of variants of one, and then we're going to talk about point 3. And it turns out this third one, you can add bias into your solution, which seems kind of strange, but this will actually improve the performance of the algorithm. And this is actually kind of this bias which creeps its way into a lot of what we do in machine learning, for instance, and not necessarily bias in a way that because the data itself has some inherent bias into it, but in that the bias tends to be towards models which are simpler, or if you're running gradient descent, you stop after so many steps. That implicitly gives you some bias in the solution. This turns out it helps, okay? And I'll explain a bit about how that works. But I just want to mention a couple of things here. Okay, so the first one is we're going to talk about, when we're talking about dimensional reduction, what we're going to have instead is points like this, and we're going to fit a model that again goes through the points. This could be lower dimensional. In regression, the model is always a one dimension lower than the kind of essentially what the data lives in. Here it could be even smaller than that. But in this case, we're going to model the residual by, this is the result of PCA, is come out the residual as the orthogonal projection onto here. Right, so that's different from up there, that's only measuring the y coordinates, okay? Where this is measuring in kind of all the coordinates systems. No coordinate is special, okay? The advantage of ordinary least squares is that it's okay if the units on xi and yi don't match. Okay, so if I look at this model, y hat equals alpha 0 plus, say, alpha 1 xi, and xi is kind of, I'm predicting weight from the height. Well, alpha is it's going to be in terms of units, weight over height. It's going to convert the units for us. Okay, so there's nothing kind of, and because the air is only measured in the y direction, it doesn't care about the units there. If I change the units of x, right, to be, you know, from feet to inches, well, that just factors into alpha 1. Okay, so it can handle different units here. The stuff we're going to talk about that add a bias into it won't be able to do this, but in the case of just the basic ordinary least squares, it can handle different units. This one can't. But it's a different model. Okay, so the other thing that, and we'll talk much more about this after break. Yep.
So you said it can handle different units, can it handle different types, so like apples and oranges type?
Sure, yeah, I can predict how many oranges I'm going to eat this week based on how many apples I eat. I can collect data and I can make that prediction. If I eat more apples, I eat less oranges. I only have so much fruit I can eat, right? You know, and there's maybe a baseline model. I always have at least 3 oranges, but inverse this to be negative, then inverse the number of apples. So you can do apples to oranges. And I can factor in pears too, and other fruits and bananas. Right? I build it into one big model predicting how many oranges I'll eat based on the apples and bananas and pears that I eat. That's perfectly reasonable to do. Right? Where in other cases, I mentioned this is not reasonable, but in this case it's okay. Okay, so that you have permission to do that for a basic regression problem. I'll point out where this breaks, and that will happen soon. But this works with polynomial regression, that's all fine. It converts it inside of the different coefficients. Okay. Okay, the other thing I could do is I could do some, okay, so there are these forms of like robust regression, and we'll talk more about outliers later, but these try and handle outliers the same way as the mean versus the median of a data set. Right? If I have data that looks like this and one data point out here, right, then I'm going to have that this is going to be the mean, and somewhere over here is going to be the median. The median has a property that half of the data is on either side. So if I put one data point out here, well, it can't move that much. It can move at most one data point. So if the data set is really grouped together, one outlier can't affect it that much. I have to, and there's this idea of these resistant estimators, which say that the median, I have to put up to 1/2 of the data points as outliers before I actually really move the median from where the real data is. If I put more than 1/2 points out here, well then maybe this is the real data, right? It's like, can't do any better than that. Okay, so where the mean is the point though that minimizes the sum of the squared distances to this point. That's the property of the mean, like we mentioned with K-means clustering and Lloyd's algorithm. So, and the mean is akin to what least squares is doing. So it's affected by these outliers, okay? Okay, so there are these versions of regression that try and do something like the median, but for the regression problem instead, okay? And so one of these is called the Thiel sen estimator. Okay, and so what this does instead is it estimates A as the median of all slopes xi minus xi prime, I think divided by y primes, yi prime minus yi, right? So it's so if for all pairs, I think maybe it does consecutive pairs based on the sorted x order. It computes all of these kind of slopes between 2 points, and then it takes the median of all these, and this is A, and then B is then the median of all the sets of yi minus a xi, right? So instead of taking the mean of this value, which was what we're effectively doing before, we're now taking the median of this. Okay, and so this, the Thiel sen estimator is resistant up to something like 27% outliers, or 29% outliers. So I can put 29% outliers, and this will still be kind of in the middle of the point set. There's versions that you can get up to 50% outliers. They're slightly more complicated. Okay, but this is kind of a completely different approach that is better with outliers. There are other ones, but this is kind of one example. Yeah.
This would be more computationally expensive to compute, is that right?
Yeah, you can do this in close to linear time in 2 dimensions still. Like you have to sort the data, but people have worked at how fast can we compute these things, and they've kind of come up with algorithms. They're more complicated, so there's probably some constant factors, but scalability, it's not too bad, at least in low dimensions. In high dimensions, this is where these really run into a problem. They become exponential in dimension. Aside from this recent work the last 5 or so years that I mentioned. And maybe we'll talk about that now in our section. Okay, so this is just kind of a couple of other things with goal 1. There are other things to think about there. But otherwise, we're going to think about basically minimizing sum of squared errors, basically because there are still good algorithms when we want to add bias, and it corresponds with maximum likelihood estimator for the Gaussian, if we have normal noise, which is pretty standard. Okay, so good. So I want to talk about, so ridge regression, so also known as, so this also known as Tikhonov regularization. Okay, and so now the difference here is my goal is going to be the sum over all the data points I, yi minus some sort of model. Right, so either I've done polynomial or I just have multiple variables squared. So this is the same as before, but I'm going to add this extra term here. Okay, so I'm going to add this extra penalty term. S is going to be some scalar value, some parameter, some regularizer parameter. And I have this penalty, okay, so this is a penalty on a complex model alpha. So alpha is my model, and this term is large when the coefficients are large. Okay, so if my model's, I'll say complex, if the coefficients of the model are going to be large. Okay? And so I want to penalize those. So I want to minimize this, and S is some scale parameter that I have to set in some way. notation, which we'll talk about next week if you haven't seen that before. How do you set this? Okay. And so, okay, so I'm adding, I want to penalize against these models which are going to be complex. And it turns out that this gets around this actually gets around this Gauss-Markov model, this Gauss-Markov theorem. You can prove that if I choose the right S, I will do better than if I set S to 0. Unless the data lies exactly on a line. If all the residuals are 0, then it's better to set S 0. But otherwise, there is a S. There is some S. There exists some S such that the ridge regression solution alpha S is better than alpha 0. Well, just call this alpha from alpha from the least squares. Okay, so this is basically on unseen data, which we'll formalize next week with cross-validation. Okay, but if you think this data has come from some unseen distribution that you've drawn samples from, there exists some S where the alpha S I learned with this model will do better than what I would find with just ordinary least squares.
How do you determine S then?
Yeah, so we'll determine it with cross-validation, and I'll talk more about that kind of next week. Basically, short answer is you hold out some of the data, and you build a model on the training data, and then on the held out test data, you test a bunch of, you build different models with different S's, and you see which model works the best on the held out data. And that's what S you use. Okay, and there's some S which is greater than 0, which will do better. You don't necessarily know what that S is. It might be very, very small, but it will do better. And you can prove this by actually writing down the gradient of this function and showing that kind of with respect to S for any data set that has residuals, and you'll see that the gradient kind of will increase. So at least when S is 0, it's going to be slightly better to increase it for a little bit. So you can prove that there's some S which will do better unless the data has 0 error in the residuals. Yeah.
Is that S similar to like learning rates, or is that what it's called?
So it's different than the learning rate. Yeah. So I haven't told you how to solve this. The learning rate goes into a gradient descent algorithm, which you can write for this, but that's kind of it's a different hyperparameter. And you don't need to use gradient descent to solve it, so then you don't have to set a learning rate. Okay, in fact, this brings me to alpha S has a closed form solution, which is X transpose X, plus S squared. Okay, so I can actually, so I can solve for the optimal solution by just adding this term right here. Before I do this inverse, I do S squared multiplied by the, so this is the d by d the d by d identity matrix. So S squared. So after I multiply by S, it's got S squared on the diagonal, zeros off it. And so one of the issues that comes up with this otherwise is that when I'm doing an inverse, if you remember your linear algebra, this X transpose X, if it's not full rank or close to not being full rank, then this is kind of a poorly defined operation. It's not going to be stable. But when I'm adding this identity matrix, I'm forcing the rank, it has to be full rank then. And even a small s is going to force it to be full rank, and this will actually make this computation of the inverse more robust. And I'm doing things less likely. I'm dividing by this, right? So divide by something which is effectively 0 is never a good thing to do, right? So if it's not full rank, I'm kind of dividing by 0. I can do a pseudo inverse is technically the right thing, to do for the ordinary least squares, which is a way to get around this. But you can do better by actually having this small term here, which is stabilizing this operation. And it turns out this is the optimal solution for this formulation at the top. Okay, so it's just as easy to solve as ordinary least squares. It's no harder. I just add in this extra term here. Okay, so it's not any harder to solve. And if I solve it with gradient descent, it's similarly just as easy to solve as before. But it's going to be more stable computationally, and if I choose the right s, it's going to be better. Not necessarily a lot better, but it's in some cases it is, in other cases it's pretty small. Okay. Yeah. So let me give you a little bit of intuition why this might be a good idea. Okay, I can think of two models through this data. One, this is alpha least squares, and this might be, alpha s from ridge regression. Okay, so this one I've chosen it, kind of ignoring whatever's going on at the offset. Assume maybe 0 goes through there or something. But this one, the slope is smaller. The slope is smaller corresponds with the norm, right? So smaller slope is equivalent basically to this squared being smaller. Okay, so when I penalize having a large L2 norm of this of the model coefficients, it's penalizing so the slope is smaller here. Okay, is what's going on. Okay, so why is this useful? If I draw the x-axis here, and I think of this, let's take this data point for instance. Say this is x1, y1. Well, that corresponds with x1 down here on this axis. Okay? And so if I move this to x1 prime, this is x1 plus delta. In this case, delta was negative, it moved less. Okay, so what's going to happen? I'm going to have two predictions here. The first one is from ordinary least squares. The second one is from the ridge regression solution. And I'm moving them kind of here based on if I added a delta onto here, I've changed it. Okay, so what is, if I look at the difference between these values, the ordinary least squares has a larger slope, so a small change in the x value is causing a larger change in the y value here. Whereas the ridge regression, the same change in x value, the change is smaller. So for instance, if I change, this model we predicated on the noise only being in the y direction, but if there was noise in the x direction, this is more stable. It's changing the prediction less. Right? So that's one of the reasons why this ends up doing better. Because it's going to bias towards smaller slope models, and those are going to be more stable with respect to air in the x direction. There are other ways of thinking about this, and we'll see some in the lecture Wednesday as well. Yeah.
So then you're saying that a ridge regression they could be more appropriate if you were trying to model something like a simulation with an adaptive time step?
Oh, because there is error in the x value.
Yeah, there's variation.
Yeah, so I mean, this is one thing. If you don't trust your x value so much, then you want to bias it to have smaller slope because you want it to be more stable as you change the x value in the prediction of the y value. Yeah, so that's That's a good way of thinking about it, yeah. So if you know there's value in and there's error in the x value because you've discretized things, for instance, then this is a good idea. Good. All right. So there are other ways that this is useful as well. Yeah.
So would there ever be a case in which you'd want to maximize the slope then? Or,
Oh, if you want to have a larger slope?
yeah, like suppose you, yeah.
There possibly could. I can't think of any right now. It's pretty uncommon. You almost always want to. There are other ways of regularizing. I'll show another one next. And it'll also be, also forces the slope to be small, right? And these are the common. There are a bunch of variants of these, and they all kind of penalize having smaller slopes, right? So this is standard. In particular, with more complex models, what a larger slope would allow you to do is actually I could have two variables which are correlate with each other, right? So if I make one larger, if one increases, it corresponds to the other one also increasing. So if I want to make the slope larger, well, what I could do is I can make one large and positive, one large and negative, and they counteract each other. And they force these really high coefficients. But the net effect is zero. But if there's small variation in that correlation, it becomes really unstable. But that's what a higher slope would allow me to do. So that probably is universally a bad idea unless I want a really unstable model. So good. Okay, so we'll talk a little bit more about the structure of this in the lecture tomorrow. Maybe I'll have a chance to say one more structural thing, but I want to introduce another way to add regularization. And this one is called lasso. And sometimes called so the algorithms associated with it are so sometimes called basis pursuit, because as we'll see on Wednesday, the ways you might solve for this actually incrementally build up a basis of your coefficients. Okay, and so this is a slight tweak on before. Now I want to have some penalty I'll call L1S. Say x, y, alpha. And this is the sum. So this is the thing I'd like to optimize. And this will be yi minus our model squared. So this term is the same as before. But now I'm going to have s. It's going to look like this. Yeah, so I'm just taking the L1 norm instead of the L2 norms. It's typically written without being squared. I think that's. Check to make sure that's not squared. Yeah. So let's say that's not squared. All right. Okay. So this is the lasso model, and all I've changed is I have an L1 so regularization. Okay. Okay. So this is not going to have a closed. Well, it has technically. There's an exact polynomial algorithm which you can run, and we'll discuss that on Wednesday briefly. But it does not have this simple closed form kind of linear algebra solution anymore, right? So this has no simple linear algebra solution for solving it anymore. Okay, I can run gradient descent on this, but the problem is this term is going to be convex, but is not going to be smooth. So it's going to have these points where the gradient is not properly defined. Okay, so if you're familiar with gradient descent sort of approaches, this one is not going to be smooth. They're not defined, but they're defined as you approach them, so they're defined on either side. So there are ways to get around this, and you can make it work fine, but it's more complicated to run with gradient descent. But it's convex, so you can still do it, and you will guarantee to converge. Okay. If you haven't, we don't talk about gradient descent in this class by design. If you want to know more, the book does, hopefully, I think a good job of explaining it, but or it's in author of it, but but it's a useful thing to see. Okay, but this has the advantage. This will induce sparsity in alpha. Okay, so this means it's going to set many of the coefficients alpha I will be exactly equal to 0. Solving for this with any reasonable s value will the optimal solution that I find for this, and there are algorithms to find them, which we'll discuss, will have a lot of the coefficients be exactly 0. Right? So that means the model says that the best model under this kind of way of writing down the cost function does not use this variable. That's what the coefficient being 0. So think of I've got a large number of parameters, and I solve for this, and it says the best model for this sets this coefficient to 0, which means it does not use that parameter in making the prediction. Okay, that's pretty cool, right? And so it allows you to do things like if there is a very simple model for certain problems under some noise conditions, you can find the exact model. Okay, and even if there are way more parameters, or kind of different dimensions in your data set, it can still find and recover the right simple model if it is simple. Okay, and so we'll kind of go in more in depth on this on Wednesday. So most of Wednesday's class will be talking about this algorithm and why this algorithm works. Okay, and why it's inducing this sparse model. Okay, so I want to give a warning though. This is not kind of a perfect variable selection. Okay, so you could think of having this. I guess light bulbs don't look like this anymore, but you can think of having this idea. Okay, so if you think of this idea, I will only select the variables as being important if and only if alpha I is not equal to 0. Okay, those are the only ones which I think are important. The rest I can say aren't important. Okay, so you can have this idea. It makes this is a very reasonable idea. And sometimes this is true, right? If I have a sparse model, and there are ways we'll talk about on Wednesday where this is exactly true. These are going to be the only true things that matter. You can define, there's some physics of a system, and I throw in a bunch of nuisance parameters, and there's no noise in it, and I can actually perfectly recover the coefficients that describe the physics of the system, right? And sometimes it works, but it doesn't always work, right? I could have two variables that are correlated. So if one goes up, the other one also goes up, right? And so let's say kind of heights and weight are correlated. Let's say those are both x values, and I want to predict kind of I want to predict the age of someone based on the height and the weight. Well, as either of them increase, the age is also probably going to increase, especially in the, when someone is less than 20, right? So if I'm looking at people less than 20 and I look at, I have X variables, the explanatory variables of height and weight, I'm trying to predict age, they're both correlated. I could probably use either one of the variables and get some sort of good estimate. And maybe I learn it with one, but it doesn't mean the other one is not useful. It just means I found a model that only used one of them. Okay, so it's not like a panacea for selecting variables. When things are correlated, it's, you know, it'll pick, maybe it'll only pick one of the correlated things. And maybe it won't pick the right one. Maybe one is actually causal, the other one is just correlated. Okay, so, and in particular, I'll mention one more thing. This, when I'm taking a norm up here, right, when I'm taking this norm, and this is also true here, I'm now mixing the units together. I'm taking some Euclidean or the L1 distance, and I'm mixing coordinates. So these all these variables, these coefficients are canceling out the units, right? So if the units don't match in the variables, they won't match in here either. Okay, so if I do this, I'm mixing units, and so this is dangerous to do in that case. Technically what you're supposed to do, and there are some things you can say about this where if all of the, if I've normalized the data so it all has kind of I think it's either a variance of 1, but and it has mean of 0, or it's all between 0 and 1, and I forget which one it is, then, and at that point I can find the correlations in the data and I can kind of at least identify them, and I know which ones are meaningful and not just because of the units, and if the units match, right, if that's the case, then it will tell me something about the optimal variable selection for this problem, but it won't necessarily tell me which ones are causal and which ones are correlated. It'll tell me the correlation, but it won't tell you which ones are causal. Okay, so don't attribute this to the necessarily right variable selection, but it's a pretty useful guide. Okay, it'll be a useful guide, but it's not 100% accurate, and don't treat it as such. So okay, maybe a quick question, and otherwise we'll stop here.
Does everything you just said about variable selection and units also apply to the ridge regression?
Yeah, everything, this same issues there.
Related to ridge regression, will the lowest numbers in ridge regression also correlate to the zeros for lasso?
Not necessarily, but they're going to be related. I'll draw a picture on Wednesday, which will help clarify how these are related to each other.